Hello everyone, it's June the 6th. Alright, so today, as always, we're going to first handle the challenge, and second, we're going to finish off the problem that we actually failed yesterday. But, I have to say, after I finished yesterday's stream, I went back to the problem, and it was solved. So, the problem is with this. It's supposed to be larger than instead of larger or equal to. When I submit the error one, I have larger than equal to. And then I realize I cannot do larger than equal to. It has to be larger because L and R can be equal. They can be equal. But we're going to deal with this later, not right now. Right now, we're going to handle this in today's challenge. Merge sorted array. It's an old problem and not that difficult. So we have two sorted arrays, right? Merge into a single array, sorry, and then this. Merge into what? Be stored inside the array num1. Should be merged, and the last one was set to 0. Okay, so we put everything back into num1, which is fine. We just like how merge sorted always does. We have two pointers, right? And if this is big, then we what? Because we have to do it directly in num1, right? So if it's small, we just keep moving, right? If it's equal, we keep moving. If this one is bigger than this, right? If this one is bigger than this, then I have to go in here. But I just realized maybe we can swap, right? We just keep, if num1 is smaller than num2, we just move on to the next one. Smaller or equal to, we move to the next one. Num1 is bigger than num2, we swap the two, and then move on. Wait, what's n? Number of elements, okay? Yeah, I think it shall work. We just try to make sure that if num1 is smaller equal to num2, we just keep moving on. If num1 is larger, then we just swap them, right? So I think at this point, this is small, this is bigger, so we swap. Num2 we don't change, and num1 keep moving forward, right? And then eventually we will have a situation where all the big values goes into num2. Let's see if it works. So if this one is larger than we have to actually know if num2 is smaller than num1, we're supposed to put something there and then we move on, right? But how are we supposed to do this? Okay, we put it there. Okay, we'll put it at the end. And then what? And put what at the end? Man, this is not as easy as I thought, because it has restrictions. Hold on. It is not supposed to be this hard. Come on. It's an easy problem. Right? We know that if it's smaller, move on, and then we have 3, and this has 2. then what? We swap them out, right? So if this, then we compare. So this is larger than, so I swap down here. So 2 comes in here. And then what? Then we compare these two. If this is smaller, then swap this down. Okay, I'm gonna do it again. So if num1 is smaller than num2, I just keep moving the pointer up. If num1 is larger than num2, then we shall go from num2, we see how many is smaller than num1, right? And then we go that many, and every time it's smaller than num1, we need to swap this, and then we swap. That doesn't make, it's still, hold on, still I don't like it. Okay, I think I'm trying to do it, and it didn't really require to do O1 space. I'm trying to figure out an O1 space, and I'm having trouble. I'm having trouble doing that. Let me think again. Think. So we find, wherever we find one that's bigger, right? And then, which means these two are smaller than these two. So I can, so we know this one is bigger than this, right? Yeah, still. All right, I'm gonna solve it using the most stupid way, which is just create. It's gonna be om plus n time space complexity, because I don't know how do you play around with this. You swapping or whatever you do. Yeah, I'm not going for this. I am just gonna say array, right, equal to, I don't care, times m plus n. Okay. Actually, we don't even need to do this way. Okay, just say equal to this. All right, and then we say ij00. Okay. So while, as usual, I think we append nums1 dot append a maximum. Yeah, this is the little trick I think I learned. You can say math.inf 2 dot append math.inf. Okay, and then we say while I smaller than m or j smaller than n. All right. Let me say if nums1 I is smaller than equal to nums2 j. Right? If that happens, then array dot append nums1 I plus equal 1. Else array dot append nums2 j plus equal 1. I think it should be m plus 1, right? Smaller or equal to, okay. Smaller or equal to. So one will land on the infinite, right? And then the other one will, because it's smaller, so it'll keep adding until that one hits. So both. So when both are equal to, okay, so actually this while is not right. Let's change this. So what we want is while this is not equal to m or j is not equal to n. So when both are equal, right, then we jump out. Yeah, so then we say for I in range m, right? We say nums1 nums I equals nums1 I equals array I, and then nums1 pop. That's it. Let's see. What? Which one? This one? Wait, why? I already append something. Which means both one can take n, one can take n. Oh, nums1's already. My bad. Nums1 don't do this. M equals nums1 m. But that's actually fine. Like, oh yeah, that's not fine. My bad. .inf. Oh, then we don't need to pop then. We have an inf. Because that's supposed to be n plus n. Why do you do this? For I enumerate. I don't know why this one gave me so much trouble today. Nums is not defined because it's not nums, it's nums1. The hell? Out of range. Oh, we have a edge case. If m is equal to 0, nums1 equals nums2. Wait, how? Okay, that I don't understand. Oh, because it didn't return. Jesus. Oh, this one. We're merging one and empty. Ew. This is nasty. This is nasty. So if it's 0, we do this. And we say if n is equal to 0, then we just return. We don't merge anything. Okay, so we have the last one. Oh, n nums1 equals nums2. It doesn't work. Why? Why would that does not work? I assigned. Of course, you reassign the name. Of course, it doesn't work. You have to put nums2 into nums1. Let's see how we can handle this more effectively. Okay, I have an idea. This is true, right? And then we say if m is equal to 0, array equals num2, else, here we go, that shall work. Num2 does not exist because that's nums2. Come on. There we go. This shall work. But still, this is not what we expect, right? It's not what we expect. I think so. This is not. It's 88, right? So this is not O1 space. So probably not the official solution. Also, we struggled a lot with the edge cases where m or n is 0. So this one is om plus n time and space. It's definitely not the one that we're looking for, I guess. But let's see. What do we have? Are they O1 space, just changing things around? Start from the end. Oh, I got stuck last time. Addition array. Yeah. Oh, this is exactly the same solution as I'm having right now. Exactly the same. So This is, so just start from the end. All right, let's see. What do you mean by start from the end? I mean from the end. We'll try to put large values. Wait, hold on. What do you mean start from the end? Are you saying both start from the end? Oh, I see. Lordy. So we did not improve on this one. That's fine. Check the solution. The trick is to start nums1 and nums2 from the end going backwards. So we are picking the larger value. Yeah, we're picking the larger value. I didn't solve this. I didn't come up with this last time, nor did I do it this time. Shame. Alright, so basically we go ij again, but that's gonna be this, right? But hold on. I kind of still want these conditions. Well, m equal to 0. Yeah, they cannot minus 1, right? They cannot minus 1. So we need to handle them separately. So I'm going to do these. If m equal to 0, and no, let's write it out. One. Then return. Okay, now we're gonna do it. Taking both minus 1, right? And then we say while I is larger or equal to 0, or j is larger or equal to 0, right? If one of them is larger or equal to 0, then the bigger one goes in. Right, the bigger one goes in, so probably need a k. M plus n minus 1. Okay. Then we say if num is 1, then I have to have all the other conditions. Like if I is smaller than 0, then nums 1 k equal to nums 2 j, right? And then j minus equal 1, k minus equal 1. Now if j is smaller than 0, nums 1 k equal to nums 2, hold on. Nums 1k equal to nums 1I. Right, I minus equal to 0, k minus equal 1. Else, and both are larger than or equal to 0. No, not both are smaller than, so one of them is larger. Then we handle this. Now this both are larger equal to 0. Then we say elif times 1k is, let's say, larger equal to nums 2j. No, not ki. Right. So the larger one goes first. So say nums 1k, nums 1i, I minus equal 1, k minus r. So we don't have to do k minus equal 1 all here. We can do k minus equal 1 anyway. So else nums 1k plus nums 2j, j minus equal 1, and k minus equal 1 at the end. So if we can see this situation happened these two times. So we say if I this, or I is larger equal to 0, or nums 1, I is smaller than nums 2j. Then we do this. Elif j this, or nums 1i is larger equal to nums 2j. Right, and then nums 1, so don't need this. And then we return, no, there's no return. Alright. Kind of bad that we have to do the testing here. Which, not really a big fan. Oopsie doozy, what the hell? We have a little situation happening. Okay, if I is smaller than 0, which means j is the only thing remaining, so we just equal to j, and j minus equal 1. Alright. What? How is this possible? Where does this 6 come from? I honestly have no clue. I don't know. So nums 1 smaller than nums 2. So k is here, equals 6. Yes, we got that. And then j minus equal 1. So here we got 5. Right, and then 3. We got 3. And then I moving forward. And smaller equal 2. Then we take this one. I come here. Right, I come here. K I think is here. Right. J is here. And then j is bigger, so we got this 2. So j is consumed. Right, j is consumed. And then the last one is here. J is smaller equal to 0. So nums k equals nums I. Come on. I don't understand. How is that? Let's print ijk. Actually, let's print at the end. And nums 1. I don't know. Like, what the hell? Oh, the k. What? K becomes minus. Hmm. Hold on. So K is 4. That's pointing this. 0, 1, 2, 3, 4. Pointer 3, pointer 2, pointer 1, pointer 0. Right? This one point to K point to 0. And now we're done. And J is -1. I is still. How is I still here? And come back again. J is smaller than 0. Ooh, I know. If I smaller than 0, and J is larger or equal to 0, hold on. Yeah, this one has to be J larger or equal to 0. If J larger than 0, and I smaller or this one. Yep, that's the first condition. And this is I larger or equal to 0, and this. There we go. Yeah, we have this condition must satisfy. Okay, this is a O1 space OM plus N time. Man, this one took so long. In reverse. I don't know why I didn't think about that. Alright, we're done with this. Back at this problem. So, kind of explain what happened. So, overall, the problem is we're trying to find, let's go to the problem. So, the problem is this, right? The problem is saying we want to find the number of subarrays that has and most k numbers of elements divisible by p. So my idea is to first find the signposts. Signposts are the indices, okay, where the value, the number, the element, I just said three things the same way, divisible by p. Okay, so we get all of them. So think about them as signposts. And then we have islands. And the islands are the area in between signposts, right? So those in between signposts, they are the subarrays that none of them is divisible by p. So the ideal is we're going to go through all these islands and count. Not count, we just put all possible, here put all possible subarrays as tuples into a set, so we don't want duplicates. But as we're doing this, we will do one more thing. That is, we will find out all the subarrays that starting from the left edge and all the subarrays that ending on the right edge. So we're going to build up these two kind of like libraries and store them in L edge and the right edge. So these are the two default dict, and you see both default dict has initial is an empty set and an empty not set empty tuple, and then we just go, you see J from L to, so L and R the boundaries of the island. And the mistake I made is initially I have this larger equal to, so we're eliminating when L and R is the same, but we should not, because L and R can be the same. That just means that the island has only one element, which is fine. So it has to be larger than, right? And then we just go L to R and then J to R, right? And then we're gonna find the tuple. We call them, whatever we call them, a temp, right? A tuple. So this tuple is, it represents all the subarrays in this island. And then we say if the left boundary of the subarray is at the L, we record it on the L edge. If the right, then we record on the right edge. So this is kind of like a dynamic program. We're building up this library. So in the future, when we are building other solutions, we can use these that's already been built. So blah blah blah. So this is basically just handling all the subarrays inside these islands, and then we're gonna go KK, and we're just like the count, right? Because these are the zero count. The zero count always we need. Then we go 1 count, 2 count, 3 count, all the way up. So 1 to K plus 1, right? So that's KK will be 1, 2, 3 all the way to K. So we say I want to find with 1. Find a subarray with only one element that's divisible by P. So that just means each signpost, right? Each signpost by itself. So we're going to say from range 1, because signpost we have a -1 at the front, so that we can standardize things, and then we have another one at the end. So these two shall not be counted. So we go from the first one, 1, all the way to the last one. So the last one is the length of signpost minus KK. So that will allow us to point to the last one. And as the KK gets bigger, the indices will move forward, right? Because we need to compute the low and high of the signposts, right? The low signposts is just I, and the high signpost is I plus KK minus 1, right? So if KK is 2, then between low and high, we have 2 signposts. If KK is 3, between low and high, we have 3 signposts. And that is the minimum length of the subarray. It's possible to have KK number of elements divisible, right? So that's the smallest, right? Smallest. So for each low-high pair, which set up the smallest length in that situation, the smallest length that contains at least that contains exactly KK number of elements divisible by P. And then what we do is we will go create the base, right? That's the baseline. The baseline is just low to high. And then we're gonna add the possibilities, all the possibilities on the right side of this. So it's going to be the right edge, well, not the right side of the space, but the right edges of the right edges of the island to the left. So we're going to find every single one of them, and also the left edge on the island on the right. So now this is where these empty things come into play, because the empty things allow us to have no right, no left, or no right, and both no right, no left. So we have all the combinations. So we just iterate through all the edges on the right or the edges on the left. We just append them on both sides of the base, and then we push it into the set and eventually return the length. That's it. We can write something down here. So this is actually a pretty good solution, right? It's pretty good, but I'm pretty sure at the same time that we'll have a better solution in the discussion. So, okay. First step, find all the signposts. A signpost is an index pointing to an element divisible by P. All right, that's the first step. Second step, iterate through all the islands in between the signposts. Each island contains only elements not divisible by p. Thus, all combinations of subarray there can be included. We build up a library of all the subarrays ending on the right boundary of each island, and all the subarrays starting on the left boundary. We will use this library to build other subarrays, right? And go from k equals 1 to kk. So 1, 2, 3, all the way to k, right? For each kk value, we pick kk, we iterate through all subarrays of signposts of size kk. And then we create a full combination of subarrays on the left edge and the right edge, starting and it's called right edge and left edge, right? That just surrounds the current subarray of kk number of signposts, right? Then we add, then we append, right? Then we add the edges to the subarray of signposts. And we're done. Runtime, I don't know. So so many, I don't even know the runtime. It's pretty bad. That's all I know. I mean, if you think about it, this, what's this? This is ON. Alright, so this is ON. And this, lordy. I call it ON squared. Maybe overall is ON squared, but I don't want to worry about that. Let's just go in here. Robbing carp. A try. Oh. A rolling hash. So this is ON to the third. Oh yeah, because we want to find out how many we have. Kind of, I don't know. I'm losing I'm losing motivation today. All right, let's just get through rolling hash. That's it. We'll go through rolling hash. We'll call it a day today. I don't know. I just don't feel very motivated today. I think it's because the first problem is kind of frustrates me. So I go through rolling hash and the try we'll see tomorrow. Maybe I'll think about it when I go to bed. Okay, rolling hash. Is it to use rolling hash to we do rolling hash on each on each uh each level basically. What is the hash? Size. Size is 0. Ah, we go through all sizes. Okay. Size is 0. And we say, this is a count. I. What is this? What is this syntax? Nums I plus size. Is starting from this. How many? Okay. Oh, this is actually quite smart. This is basically a counter, right? It's a counter. And we say we're starting from the first with length 0, right? Then how many do we have? And each time we just add 1. And if it's equal to 0, then we just increment. And if this is smaller equal to k, then hash I equals hash I times 200 plus this. Wait, is that a generic way of doing hash function? Actually, I don't know what type of hash function I should use. It's times 200 and plus the newly added value. Wait, what's S? Dot insert hash I dot second. I don't quite understand, but I know the count. Okay, the count is the count number of uh, elements in the stretch that's divisible by this, and then we use a hash. Hash is the previous hash, right? And then plus the new value. Previous hash plus the new value. And then maybe S means a set. I don't know what S stands for. But we'll insert this hash. Okay, we'll insert this hash. And oh, S is the unordered set. Why would you want to do it? Let me just insert it and just keep inserting and then handle the size at the end. This is actually too smart a solution. Yeah, I don't really know what would be like a generic way of doing rolling hash. And I don't think it's just. I think we should try to see collision check. What if it collides? Hold on. What was some that we pick a prime number that can cover the entire value space? Why did they use 200? The length is 200. So for each one, a most is 200. Okay. So to prevent colliding, we just want a scheme that can produce more than 200 values. But how does using this one help? It's like you can mod. I just want like a easy, simple rolling hash function. That doesn't. there other rolling hash? Then check hash collision. So basically, I think it is to produce all. Yes, I think it is to produce all of them, right? And for each level, because each length, I'll reset the set and I push those values in. But a hash function, what type of hash function? Yeah, we can do that. We can use that, which is a polynomial. But it can get pretty big. So I guess you just pick any. Now it's every value I'll multiply by something and then plus the new one. So the collision will happen if maybe we can do the position as well. We should. Robbing carp. But still, that solution is quite smart because at each level you need to know how many there are, right? How many there are, because you can't just produce all of them. I mean, technically we can produce, right? We can produce all of them, and as we produce, we need to know the number earned accounts. We can actually keep counting. What time is it? I don't know. Do we do this? Do we do this? All right, let's just do this. Robbing carp, rolling hash to achieve O(n) squared. All right, so here's what we do. Okay. And if once they reach k, we just don't keep going. For I in range, okay, n equals line nums. So for I in range n, j in range, I don't know, what's the j range? Huh. I want to try my luck. So for j in range I to n, okay? So we have this, right? Every time we have this, and we say count is a 0, right? And we're gonna go from I to j, right? We say count hash ha equals 0, right? So the hash function, we will take care of the starting point, the end point. So we multiply the starting point we'll multiply the endpoint. Right, we'll multiply star, multiply endpoint. And so the sum, multiply the star, and multiply the end. Okay, multiply the star plus 1 and the end plus 1. That doesn't make any sense. Well, hold on, it does. So we're just gonna go index plus 1 times the actual value. How about that? Okay, so for j in this range, we say if nums j mod p is equal to 0, right? Then we can say count plus equal to this. Okay, we say if count is larger than k, then we break. Don't keep going. Otherwise we say ha plus equal to nums j times p plus 1 times j plus 1. Right? We don't know. We can actually say to prevent a 0 situation. I'm not sure if they can take on 0. Maybe they can take on 0. Numbers, number cannot take on 0. Okay. So we say this times this. That's my hash. Will it work? Not sure. Okay, we can just like square it. How about this? We square it, so the difference gets even bigger. And then we say rest set dot add ha, right? And then boom, 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 keep going. Every time we go 1, we go 1. Okay, so that's done. And then return len rest set. I'm not sure. Does that work? Oh, it doesn't work. The hash is not good enough. The hash is not good enough. We have, wait, no. No, the hash is no, the hash is too good. That's why. Well, how do we create a hash? Position, not this, but position. So we have to do position, which means, because this is from I to j, so j minus I. How about this? Position, right? Because we want the two string of the same, not two string, two subarray of the same content have the same value. And then this is kind of my rolling hash. And I can do HA is this, right? So the hash is value multiplied by relative position squared. I'm not sure if it can work, but can give it a shot. Hey, we have a error answer. We can try that one. It might work. not good enough, the hash function. Oh man. So it's not good. What do we do? Yeah, we hash the same value. Just give it a shot. I don't know. Okay, we just raise to higher power. Hopefully we'll. Oh. Okay, what's this hash? P to the n minus 1 power. P to the n minus 1 power. What's n? That's the length. What's p? P equals 31, okay? So 31 to the power of j minus I. Okay. Oh man. Gordy. Maybe we need a mod. I don't know. This work? Nope. So we need a bigger. What, 91? Okay. 91 works. Oh! What the heck? Wait, how many? 91 still doesn't work. Give me a prime number. I don't know, like which one shall we choose? A large P. Okay. Let's choose 11111. Okay. 1111. 11111. Jeez. How long is it gonna take? You gotta give it to me. You gotta give it to me. My God. So maybe what we can do is, because that's just the power, right? And at most we can say powers is equal to, because from 0 to at most 200, right? So this minus 1, 0, okay, 0 is fine, times 200. And we say if powers j minus 1, j minus I is smaller than, is equal to 0, so if not, then powers j minus 1. Kind of do some dynamic programming. So we do this. All right. I might as well just do this mod. And then we say this times powers j minus I, and then mod. Not sure. I think this one might be faster because we only calculate them once. Oh, ooh, look at that. Look at that. So 2 tricks, right? 2 tricks here. Oh, that's something we can do. First, according to this article, a typical prime number used for rolling hash is quite big, such as 1 1 1 1 1, right? 5 ones. Now computing the second computing 1 1 1 1 1 to a large power is time consuming, right? And since we will encounter the same, we'll encounter 1 1 1 1 1 raised to the same power multiple times, we can use a DP table to store, right, to calculate, to compute the power only once. So this, these two tricks combined, allow us to reach a performance of, drum roll, that's actually pretty good performance. That's O(n) squared. Yeah. Okay, so that's that. It's actually good. I think I can talk about this in the channel tomorrow. This is just overly complicated. Do we post this? Yeah, I can. But no, I think this is good. All right, that'll be it. We will think about the trie solution tomorrow. All right, I'll see you guys tomorrow. Adios.